Good afternoon, and thank you for the nice introduction. So just before we move on to the presentation here, kind of an introduction of our group. We are a pretty new group at Sanofi. As Simon mentioned, Fadi was initially at Pfizer. We are about 2 years, and I was part of the team that started with the group. We are primarily focused on early development, but we do support late stage activities primarily. We support at this time early discovery to phase 2B. We are based out of Cambridge, our new site. And so one of the focus areas of our group was how we can use or leverage minimal in vitro assays with PBBM, physiologically based biopharmaceutics modeling, and understand the influence of parameters, in this case specifically precipitation, on effect on clinical profiles of weak-based compounds. And I'm showing one of the case studies here of Sinarezin. We've done a lot of other molecules as well. So that is going to be the focus of this work. I'm happy to share that if you need additional reading and information about the concept or approach or framework that we are using, we recently published this work in AAPS PharmSci just last month. So the plan for the presentation is I'll give a very quick background about the sources of variability that can contribute towards clinical variability, then how we use just a couple of in vitro assays from solubility and precipitation data, and then the existing PhysChem properties or details about the drug substance, drug product here, and use modeling tools, in this case GastroPlus, and then we've gone ahead and used other tools like GPROM, SimCip as well. But in this case, we are going to show you with GastroPlus how we build an oral absorption model and then tie in the influence of precipitation for the variability in the clinical response for Sinarezin, which is a weak-based molecules. We are focusing more on weak-based molecules here, primarily because they have a tendency to precipitate as they transit from the gastric environment into the intestinal medium or intestinal tract. And their profiles are highly dependent on the pH, the solubility profiles, and that's why the key focus of weak-based molecules here. And finally, ending with some summary and key learnings. So the next 3 to 4 slides will focus on some of the variabilities here. So on the left here, there's a literature that came out recently on sources of individual differences in the drug how the drug metabolism enzymes they contribute towards sources of variability. And as you see in the graph here, there are both intrinsic factors that are related to the individual or the patient, and there are some extrinsic factors like smoking, diet, alcohol use, environment, or drug-drug interactions that may contribute to variability in the clinical response. The one on the right here, it's a fairly recent paper as well, which talks about various steps into oral absorption and what factors contribute towards variability or can contribute towards the variability in the clinical response in patients. And it includes both factors contributed by the drug substance properties, drug product properties, or even related to the physiological parameters or physiological variance observed in the humans. And how and where is this study based out, and how we arrived at choosing precipitation as an option? So recently in Europe there was a study done called Orbito study, where an industry consortium had done a clinical assessment of what factors influence clinical variability, and some of the data is presented here. The one on the left is primarily the influence of transit times that are two different examples here. One is a Bravo pH capsule on the left, and the one on the right is a tablet that is coated with Udragit S100. So you may see this was done in about 8 healthy individuals that are fasted subjects, and you could see that how much variations is observed in the transit times for these two formulations. So that's first variability. The second one is the fluid volume, which is the graph on the right here. And this also shows us that there is contribution or variability because of the fluid volume as well. Then this particular slide talks about how the differences in buffer capacity, pH, and the solubilization, specifically in the upper part of the GI tract, could lead to clinical variability. So the graph on the left is specifically about the buffer capacity, especially in the upper part of the small intestine, and the one on the right is the influence, both in the first top graph is the fasted state, and the below one is the fed state influencing drug solubility. And the one that is of prime importance for our work here is that was done is the first three graphs are the fasted state, and the bottom three ones are for the fed state. The one on the left is stomach pH, and the extreme two are the distal duodenum. So specifically, if you see in human patients or clinical samples, there was a variability in the pH as well as the bile salt concentrations, both in the fasted and fed state, which became one of the questions for us to evaluate precipitation in various bile salts concentration, because there is variability in the bile salt concentrations in humans, specifically for weak base compound. So using this particular study as a basis, we devised a framework that we potentially use in our early development screening of weak base drug substance drug product. So what we have done here is we only gather two sets of lab-based data, which is using shake flask method. We calculate the solubility at different time points, and then we do in vitro precipitation in simulated intestinal fluid, specifically in this case of weak base, using Pion microdisc profiler or other precipitation equipments that are available. So just with two in vitro data sets. Then we build a GastroPlus model where predominantly we start with the drug properties like solubility, PK, pH, as well as permeability values. And if there is an existing clinical data that is available for the drug product. In the case of Cinnarizine, it does not have any IV data available. It has oral tablets and capsules. So we directly use the PK plus module, and this is a very old study. They have a 25 milligram Cinnarizine capsule that was used in this study, and we extracted the oral profile as well as the PK parameters, that is Cmax, Amax, AUC, and lambda max, Tmax. And then using this, using these as input, basically the Fischem properties or the solubility and precipitation data that's gathered in the lab, we build an oral absorption model and see whether there is prediction as well as influence of the precipitation at various bile salt concentrations on the oral absorption profile. So, and then use that as the basis to develop a population PK model as well as analyze parameter sensitivity analysis as to what other factors can play a role as well, and hope to see an in vitro, in silico, in vivo correlation of these factors on the clinical response. So what I'll quickly show you is the data that we have generated for in vitro solubility and precipitation assay. So we use a traditional shake flask method. We incubate excess amount of drug for either 4 or 24 hours, in this case Cinnarizine, in FASIF medium, that's biorelevant, at different bile salt concentrations, or we use a buffer as well, FASIF buffer. And then we perform HPLC based analysis to calculate the solubility of Cinnarizine at different time points. So if you see this table here, there's two time points, 4 hours, which is the kinetic solubility, and 24 hours. And we evaluated solubilities at 4 different FASIF concentrations. We label them as 0.1x, 0.2, 0.5, and 1x, and the description of the bile salt concentrations is in the table below. And the reason of choosing this bile salt concentration is to cover the range at as much as possible of what is observed in humans clinically. And we see at 4 hours, there's a concentration dependent increase of the solubility of Cinnarizine as the bile salt concentration increases, about 3 to 10 folds as we grow from 0.1x FASIF to 1x FASIF. And same trend is observed in the 24 hours. One information that is useful here is Cinnarizine has a very high solubility at pH 2, and it has a very poor solubility as it transits or reaches a pH of 6 or higher. And that's a similar trend that we saw here. So what we took as a message from here is Cinnarizine demonstrates about 3 to 14 folds increase in solubility. That's bile salt concentration dependent, specifically in the range of 0.3 to 3 millimolars. Interestingly, because it's so poorly soluble, we were not able to estimate the solubility at 4 hours for pH 6.5 buffer. And then we have a unique precipitation assay that we have designed where we use an infusion pump at a predetermined rate and volume. And we have the infusing medium. In this case, it's a gastric fluid, pH 1.6, where cinnarizine has the highest solubility. We infuse that into different passive mediums as shown previously from 0.1, 0.2, 0.5, and 1x, and measure in real time the concentration that's precipitated using Pion microdisc profiler, as well as we do HPLC analysis just to have a benchmark comparison with both the methods. So we expect to see whether there is a precipitation of the drug substance, in this case cinnarizine, or not. So this particular graph shows the precipitation in just passive buffer. There is no bile salt concentration here. As we may see here, the cinnarizine reaches a target concentration of about 120 to 140 micrograms per ml very quickly, but crashes out very fast within 5 minutes, and then stabilize it at around 30 to 35 micrograms per ml. So it precipitates very quickly in pH 6.5 buffer. Now when we study the precipitation in different passive, the ones that we studied the solubility, there are 4 different trends observed here. So the blue graph, the green graph is the passive 0.1x, blue is 0.2x, the orange is 0.5x, and the black one is passive 1x, which has the highest bile salt concentrations among the 4. And we see a concentration dependent precipitation profile as well. So in all of the 4 passives, it reaches almost the similar peak concentration of around 325 to 350 micrograms per ml, but then eventually crashes out very fast, and then maintains a concentration, specifically in case of passive 1x, which has the highest bile salt concentration, around 252 to 60 micrograms per ml. So what we observed from this experiment, that is an in vitro estimation, is it shows a concentration dependent precipitation profile at different bile salt concentration. So using these 2 in vitro data that's generated in the lab, as well as the physical properties of the molecule and the drug product specifications of the clinical data that we have available. So it's a weak base molecule. It has a very poor solubility, as you see here, about 1.4 micrograms per ml at pH 6.5, and it's a dye base. The data that we have used in our oral absorption model is for an immediate release tablet that's available in the market. It's for 25 milligram, and these are the parameters that we extracted from the study, the PK parameters, the clearance, the distribution rate constants, the volume of distribution as well. And then these are some of the GastroPlus input parameters that we use. Of importance here is the precipitation time, which we've calculated through the in vitro precipitation assay for different passive concentrations. As you may see, there's a difference in precipitation time at different bile salt concentrations, starting from 360 seconds for 0.1x to about 840 seconds in 1x concentration. And this study was reported for a 24-hour time period. So using all of the inputs, the drug product parameters, the physical properties, and the solubility and precipitation value, this particular graph shows a comparison of the observed versus the simulated plasma profile of cinnarizine immediate release tablet, going from the left through the right, that is 0.1x, 0.2x, 0.5, and 1x. The dotted ones are the observed data in vivo in humans, and the one in line is the simulated profiles. As you may see here, the 0.1 and 0.2x, they do not show a good correlation, but are still within the average data that is reported in humans. One challenge with this particular reported study was they did not report individual data in the patient. They reported the average values, that is mean plus or minus standard deviations only. So it became challenging as to how do we evaluate if the individual data is not available. But in case of 0.5x and 1x, we see a very good correlation between the observed versus the simulated profile. And that was our take-home message for here, that for 0.1 and 0.2x, although the correlation is not that great, but it's still within the average mean plus or minus standard deviation. But we see a good correlation for the 0.5 and 1x profiles. Now, this particular data that's shown in the previous slide, this was specifically done at a particle size of 25 microns. and that's the default setting in GastroPlus if you don't change. The reason of evaluating those, evaluating at a different particle size, which is basically the interest in this slide, is we saw precipitation and potential redissolution of the particles, and we wanted to evaluate whether there is a difference in when we change the particle size in any estimation or simulation profile for synarizine. So it's the same way, the 4 graphs for 0.1, 0.2, 0.5, and 1x. These are plasma concentration versus time profiles. The blue dots or circles are the observed concentration. The orange one is the plasma concentration that's observed at 5 microns, and the black one is at 25 microns. And we see that in all the 4 cases, there's actually over prediction of the observed with respect to the observed when we perform the simulations at 5 micron particle size. And this is just not the case with one particular concentration, but most of them. And between both, as we compare between 5 and 25 micron as well. So having built the oral absorption model and done or studied the effect of particle size, what we wanted to see is what other factors or parameters are key or should be considered in studying our oral absorption profile. So this particular slide here is evaluating 6 different parameters. So precipitation time, solubility, permeability, the pH of the stomach, the pH of duodenum, as well as the particle radius on 4 key oral absorption parameters, which is the one on the left top is oral FA, that is fraction absorbed, which is of interest, then Cmax, followed by Tmax, and area under the curve, that is the graph D. So it's kind of a sensitivity analysis to see which of those 6 factors or parameters influence these 4 PK parameters or not. So what we found is, since we were doing precipitation study, for us precipitation time higher than 650 seconds, which specifically is observed in the case of FASIF 0.5x and 1x, is essential for Cmax because it affects that, but not the area under the curve. The ranges for these are, the ranges of the 6 parameters are chosen depending on how the physiological conditions are clinically observed in humans and those reported in the literature as well. So this further validates that there is influence of precipitation time on Cmax, which is observed also in the oral absorption model that we built, but not the AUC as was seen in the case of the oral absorption model. And this one, so how does this correlate to the in vivo absorption and dissolution? How the influence of this oral absorption model that we have built affects or correlates with absorption dissolution profile. So specifically for the FASIF, this particular graph here talks about 4 different FASIF concentrations, starting with 0.1 on graph A, 0.2 on graph B, 0.5 and 1x, and there are various colors here which denote either the amount that is dissolved, permeated, or absorbed. Specifically for 0.1 and 0.2x FASIF concentration, as we may see from the graph here, there is rapid absorption and dissolution, and then potentially redissolution of the particles, as well as there is slight difference in the case of 0.5 and 1x. And so what we take home from this particular observation is, specifically for 1x FASIF concentration, the absorption process here could be potentially dissolution or solubility limited, and that's why there's an extended absorption phase that we see in the graph D here. That's not the case for FASIF 0.1x and 0.2x concentrations. Now the next couple of slides will talk about how does our model, the model that we have built, how does it perform. So there are 2 parameters that are predominantly used in terms of understanding the performance of the model. First one is the average fold error, and the equation is mentioned on the bottom slide here, which says how are the predicted values, are they over-predicting or under-predicting with respect to the observed values. And the second one is the absolute average fold error, which is basically quantifies the above value, the average fold error from the true value. And the equation is on the slide here. So when we study for Cmax, for AFE, that is average fold error and absolute average fold error, for the different FASIF concentrations, we get a range of values from 0.68 to 1.01, and this does not have a unit because it's a ratio, and there's different categories as well. So anytime the AFE is or AFE, those absolute fold error and average fold error, they are in this range. They come under the category of satisfactory. That's the minimal that's the maximum you can get. Or if it's higher than 0.85, which is the case for FASIF 0.5x and FASIF 1x, it's called passable. So it indicates that the model did a decent job in terms of its prediction ability. And the similar trend was seen in case for the AUC as well, where both the average fold error and the absolute average fold error, they did demonstrate either passable or satisfactory in terms of its performance. So finally, having done this, when we were working on this, we got a comment from our team that, how does this correlate, because we have not analyzed this on an individual patient databases. How does it correlate when we do a population PK, or when there is a large subset of population, or how will the model perform? So we did perform a population PK estimation as well, using around 3,500 subjects and default settings that are available in GastroPlus. So the first graph here is the observed and predicted Cmax, both from the single study that we did, that is basically the data that I have shown, as well as from the population PK. And the one on the right is the AUC, both from the single and population PK. So the extreme left is the observed data, that is the average mean plus or minus standard deviation, then followed by the predicted Cmax for different FASIF. So the black circles are for single simulations and the blue circles are for population PK. So if you see here, the Cmax that is either predicted or estimated using the oral absorption model, both for single and population simulations, they are within the average mean or plus or minus standard deviation, meaning there is potential influence of precipitation on Cmax at different FASIF concentrations. But that's not the case in the case of AUC, because they are more or less within the same average values for what is observed in the clinical study. So again, for the same observation, there is influence of precipitation on Cmax, but not AUC. So in summary, what we have done here is we studied the influence of bile salts variability on solubility and precipitation rate for one weekly basic compound, cinnarizine. Then the GastroPlus model that we built, it resulted in a considerable correlation with the observed profiles, as well as the PK parameters, specifically the maximum plasma concentration, that is Cmax. And the mechanistic modeling, that is the bottom approach that we used here, of using just 2 in vitro experiments, was able to predict the clinically observed plasma profiles in the case of cinnarizine. And we have gone ahead and done this for other compounds, weekly basic compounds like dipyridamole, carbamazepine, some in-house Sanofi assets as well, and they tend to report the similar data as well. So what are the key learnings for us and how we use this? So specifically in early development at Sanofi, what we are interested is what is the minimal amount of experiments that we can do specifically in early development, because we are curtailed by the amount of drug product that is available to us. Is we basically need the Phys-chem properties of the compound, the potential drug product that we are going to have, and solubility and precipitation data to predict whether there is going to be an influence of precipitation in clinical response or clinical profiles in humans. So it can provide us the biorelevant information which can be integrated with modeling at a very early stage, and rather than going back and forth later on to see, okay, this should have been taken into account. We can screen different formulations and drug substance, help thereby gain more understanding into the in vivo behavior. And finally, help early stage biopharm scientists to evaluate various unknown parameters. Specifically, in this case, we evaluated precipitation for the drug substance or drug product. With that, I would like to acknowledge Fadi, who we both are part of the team. We are growing. We are a pretty new team, as well as other members of Sanofi. And I'll be happy to take any questions.
Cool. Thank you for the presentation. I just wanted to know, what were the implications of your findings in terms of your formulation team? What were like some of the, what was the response to these findings, and what's the impact, basically?
So the immediate steps that we, like what we can keep in mind is, first is we need, what is the minimal amount of information or experiments that we should take to, specifically when we have weak-based compound, and precipitation can play a role. The second being is how can we enhance supersaturation and inhibit precipitation. So what excipients or modifiers we would need to involve in our, let's say we have an oral formulation like spray dye dispersion or ASD to enhance that supersaturation and inhibit precipitation. So part 2 of this work is actually what we have not disclosed here is what we are screening, we are developing a library of excipients that can act as a precipitation inhibitor, enhance the supersaturation. And this is part of a broader concept of using molecular modeling, biopharm modeling, and minimal in vitro assays to help formulators overcome the challenges when they are working with the weak-based molecules. So help with excipient screening or what concentrations they should be focused on. So those are a couple of immediate impacts that we are working on or helping in with the formulators.
Okay, and one more question. Let's say you had seen this variability in the Cmax later on in the project. Having the model that you have developed right now, is there any solutions that would come to your mind as troubleshooting, or?
So one aspect or one step that can be taken into account is trying to understand individual patient level data and where the variability is coming on, and kind of back calculating a back understanding of what factors might have contributed towards that variability in Cmax. And retrospectively doing the analysis. I don't know if that answers your question.
Any other questions for Siddharth? No? Okay, thanks very much, Siddharth.